professor at Ohio State University. He was one of the core faculty that established the OSU Sustainability Institute, and he also leads the university stormwater management program. His EcoTalk will be monitoring an H2O Ohio wetland in Clermont County, performance of a floodplain riverine wetland for runoff treatment. So let's welcome Ryan for his talk.
Good to see you all here. Thanks very much for coming this evening. Excited to share with you some work that we've been doing over the last 2 to 3 years about a wetland down in Clermont County, which is the county just to the east of Cincinnati, if you're not familiar. How many of y'all have heard of the H2O Ohio program? Okay, fair number, so a little bit more than half. So this, just if you're not familiar, this is Governor Mike DeWine's program to implement wetlands across the state, among other sort of management practices to control pollution, particularly pollution in water. And so this program, I think at this point, has resulted in the implementation or restoration of many dozens of wetlands across the state. Most of those, as you might imagine, with the algal blooms in Lake Erie, are sort of up along the lakeshore. But there are some sort of scattered across the state, including this one that you'll see tonight in Clermont County. I just want to thank mainly Sarah Valentine, who's actually a resident of the Dayton region, who was the master's student on this project. She finished up and defended her master's back in May. She's an awesome student and collected and analyzed a lot of the data that you'll see tonight. And then Jay Dorsey, who's a research scientist in my group, who's worked in stormwater for decades in Ohio and was an integral part of the project as well. So I'll just give you a little bit of background. I'm going to start with some background, kind of hopefully some locally relevant Dayton background, because we have done some research here in Dayton in the past, and then we'll jump over to Clermont County. So if you're thinking about stormwater, particularly urban stormwater, right? Really, it's the land use conversion from an agricultural or a forested or a meadow type condition that we might have before we urbanize. And then what we do is we build impervious surfaces, right? The road that you drove on to get here, the roof that's above us hopefully is impervious, right? Otherwise, we've got a roof that maybe isn't functioning as well as we hoped it might. And what this does is it translates more rainfall as runoff. Right? It fundamentally changes the water balance that was here before we as humans arrived. Okay? And so a lot of what my group does is field research, applied research out in the wild, if you will, outside of the laboratory, out in places like this metro park, where we think about how can we implement controls to get the rate of pollution discharge back to something closer to pre-development. Okay, back to something that approximates that meadow or that forest that would have been here in west central Ohio before we urbanized. Okay, so my research group works mainly with folks like metro parks, communities, ODOTs, ODOTs of the world, City of Cleveland, City of Columbus. We've done work with Cincinnati, Dayton, among other places. Right, so we're out working with communities to help them to try to better understand how to manage things like the flooding that you see here along the bottom, right? Like the stream erosion that you see here. This is a human, right? That's inside that stream channel that's really cut down from all the erosion from the urban areas and the watershed. So these are the types of questions that we think about. And there's fundamental shifts that are happening, right? You may be aware that we've gone from a primarily agricultural society, primarily agrarian society, to now having a primarily urban population, and that shift is continuing to head in the direction of more and more urbanization. And so this idea of stormwater being a problem is only, I think, going to be exacerbated into the future. For example, it's hard to see this graphic, but this is the Ohio River watershed here. This is 1970. Sorry, this is 1920, 1970, 2010, and then a projection out to 2050. The red areas are those urbanized areas, right? So you can just see how much bigger those urbanized areas are getting over time, and therefore stormwater is an issue. The last time that I was here at EcoTalks was a couple years ago, and that talk I gave was around this idea of how land use impacts water quality, okay? So these are all pictures actually from the Dayton region, different watersheds that we monitored here in Dayton, where we looked at a single primary land use in each of these watersheds, be it commercial or single-family residential, industrial, and the like. Okay? And the whole idea was, can we understand how pollutant transport is happening across these different land uses, so that we can then inform management down the road. Okay? We'll jump in and look at a little bit of data on that in just a second. But before we do, I think it goes without saying, we also need to think about how we develop, right? As we create more and more impervious surfaces, we of course create a worse and worse stormwater problem. We get things like the urban stream syndrome happening, where we lose a lot of our benthic communities, we lose a lot of our fish, we lose a lot of our habitat because of the erosion that ensues. This, as you might be familiar, is Cuyahoga County. I'm struggling with my words tonight. Cleveland, right? You can see a post-World War II look at the urban areas. The red areas here are urbanized in 1948 on the left, and then about 20 years ago on the right. We've more or less entirely developed out Cuyahoga County, and if you're noticing the numbers there, it's a net population increase of about 4,000. Right? So the ways in which we urbanize and the ways in which we use our land fundamentally change the water management needs and the stormwater management needs particularly. The other piece of this, of course, is the more extreme weather. What am I supposed to call it these days, right? Climate change, right? The climate change that, if you look at the data, you don't even need to project out into the future. If you look retrospectively, it's already happened, right? It is already here. We have more intense rainfall. We have more rainfall in parts of the year, particularly that spring period. And then, at least the last 4 years in a row, right, we've had a huge drought in August, September, first half of October. So our rainfall patterns have already fundamentally shifted here in Ohio and in other parts of the country as well, right? I used to work in North Carolina, lived in North Carolina for about 10 years. You can see the two events that came through in 2024, right? This is Helene on this side, and I've now forgotten which hurricane it was that came through eastern North Carolina. But you can see between 20 and 30 inches of rainfall there. We're talking feet of rainfall, right, in a single event, twice in a 2-week period in one state, right? So we have not only a water quality problem, we also have water quantity problems. We either have too much or too little, right? That problem of overabundance or shortness of supply. So these are all things that my team sort of grapples with. I wanted to share a little bit of Dayton region data, just because I thought you guys might find it interesting, since you probably live and work near here. This was a former student, Ian Simpson's work. Again, he was looking at how land use impacts water quality. So we have all these different watersheds, 3 single-family residential, 2 low-density residential. Those are sort of larger lot, 5-acre type lot residential, multifamily residential, industrial, commercial, parking lots, and then a couple of forests that we monitored as well to try to look at how the urban areas are different from our pre-development condition, if you will, to try to see how much we've changed pollutant transport and runoff response in these watersheds. You can see maps of the watersheds here, right? It's a pretty standard single-family residential watershed here. Some industrial sites. These are all either in Kettering, Springboro, or Xenia. And I realize Xenia maybe isn't quite Dayton, but sort of in the region that we have. Okay. And what we did is we instrumented the sewer system, so the storm sewers, not the sanitary sewers, not the wastewater sewer, but the storm sewer, to be able to measure flow and take water quality samples. So we have rain gauges that we put into each watershed, and then this is actually the equipment in the sewer system itself. We have a little strainer here where we can actually suction samples using a pump, fancy pump essentially, and then we have a flow meter here, so we can measure the flow rates over time through that sewer pump. Okay. And what we did is we instrumented at the outlet. I'm trying to find the outlet of this watershed. It's up here, the green triangle. We instrumented at the outlet so we could tell exactly what was coming off of the watershed as a function of time. And then we have a fancy sampler that we use to run off of a boat battery and solar power that we use to take samples during the rain event, so we don't have to be out there and get struck by lightning or whatever other negative consequences you might have if you're standing in a rainstorm. And so the nice thing about these samplers, and this same idea is what we did at the wetland I'll share in just a second, is we're able to take these green dots are samples across each runoff event. So we're able to kind of get a good average pollutant concentration across the event, okay? Because we're able to use the flow to trigger the sampler that you see here to pull these samples across the runoff event. Does that all make sense? Is that all good? Okay. All right, so this is a lot of data on one slide. I'm going to try to boil this down for you to the brass tacks, okay? So the whole idea of this is we get a pollutant concentration, say, 2 milligrams per liter of nitrogen, for example, right? And then we're also able to measure the number of liters of water that came through that sewer pipe. Okay? Follow me there? So milligrams per liter, you multiply by a number of liters, you come up with milligrams, right? Come up with the mass of pollution that was discharged during that rainfall. That all make sense? Okay, so this is that mass, okay? And I just want to share with you kind of how does different land uses affect this? How does urban compare to forest? How does that compare to agriculture? Okay? Because those are fundamental land use management questions that we have to make as human beings in the modern world, right? And as stewards of our lands, okay? So I'm going to look at nitrogen and phosphorus particularly because those are our big drivers of algal blooms. This Tn is total nitrogen. This Tp here is total phosphorus. I'm just going to focus on those two columns, okay? I'll try to hold this down. So forest, right? 0.55, roughly 0.55 pounds per acre of phosphorus per year. Sorry, nitrogen per year from a forest is what we monitor. If we compare that forest to agricultural watersheds, which this is not our monitoring, these are data from the literature, you can see we've gone from about 0.55 up to at least 10 times that, if not more like 20 times that, okay? So if you've heard nutrients are the problem in Lake Erie, in Grand Lake St. Mary's, and pick your inland lake, I'm not here to tell you that nutrients from ag aren't. It's an issue, right? It sure is, okay? So for nitrogen, you can see the differences there. The interesting thing, what we found in the land uses that we monitored, these ones that I'm bringing up here, those are all our urban monitoring sites. And what you can see is the pre-development condition is still much, much less than any of these urban land uses, right? And the other thing you can see is in some cases, like commercial, parking lots, heavy industrial, we are not that far from the nitrogen coming off of an ag field. And the reason for that is we just have so much more runoff coming off of our urban areas, right? Almost all the rainfall becomes runoff. So even if you have a small concentration, your mass of pollution is still quite high, okay? The same story is true for total phosphorus, so about 0.14 pounds per acre for total phosphorus from a forested condition. Roughly 5 to 10-fold that for agriculture, so sort of a little bit lower, not as extreme a difference as it was for nitrogen. But what you can see in the case of urban areas is in some cases our phosphorus in urban areas is actually worse than agriculture, right? Particularly for parking lot, heavy industrial watersheds that we monitored. There was more phosphorus coming off of those than there was from the ag fields, okay? So as we go from sort of a pre-development condition to agriculture to urbanized or suburbanized, this phosphorus problem is not necessarily likely to go away. Okay? So that's a challenge that we have to deal with as managers. So one of the ways that you can deal with this problem is constructed stormwater wetlands. There are a lot of others as well, but wetlands are particularly good because they work in our poorly draining clay soils that we have in large portions of the state of Ohio. And I realize there's some glacial till soils here in the Dayton region that drain quite well, but in large portions of the rest of the state, we have clay-dominated soils that don't infiltrate water very well, right? So these are also particularly good in high water table locations, so areas like Toledo, where you've got a water table that the seasonally high water table might only be 12 or 18 inches below ground surface, right? very, very close to the surface. Those types of areas work very well for wetlands. These systems obviously employ wetland vegetation and wetland soils to process things like nutrients, heavy metals, and other pollutants that are transported in runoff. So they've been quite popular, including in the H2 Ohio program that I mentioned earlier. The Governor DeWine has really championed, I would say. So there's a couple types of, there's more than a couple types of wetlands, but I'm just going to share with you a couple here, just to give you an idea of some of the ways in which you can control or manage runoff. This is one example. This is a wetland that we monitored and actually designed and had constructed up in Superior, Wisconsin. If you're not familiar with that area, this is across the river from Duluth, Minnesota, on the western tip of Lake Superior. And in this case, we were actually working at a marina. The marina is sort of off here, off to the side, drains down into this sort of area where we were able to take the velocity out of the water. This idea of the foremay is there to slow the flow and accumulate solids and trash and other debris that's coming off the watershed. And then we have two wetland cells, one here and then one here. And then at outlets, this is actually Lake Superior. Okay? So this is what we call a flow-through wetland, because the water comes in at a defined inlet point, flows through the wetland, interacts with all the beneficial wetland processes, and then there's a defined outlet. Relatively simple. Yeah, I'm going to move through the rest of this. That's for more detail than we need here. Another type of wetland that's out there is this idea of a floodplain wetland. And historically, we had tons of these, right? Every river across the eastern part of the U.S. and large portions of the U.S. in general had these floodplain wetlands adjacent to them, right? Because of the way that we have managed our river systems, which if you think about the Ohio River, we manage it largely for navigability, right? So we can move goods and services up and downstream. What that does when you put those levees and dikes in places is it separates the river from its floodplain. So by and large, if you think about the Mississippi system as another example, we've lost tremendous amounts of floodplain wetlands, which were there to serve as a buffer for the big flows when the floods came through, right? So this is an example of, and this is not in Superior, Wisconsin. That's my bad. That's a result of me not having enough time to modify this slide. It was a day today, folks. It was a day. I didn't have enough time for myself to modify the slide. This is the one in Clermont County here in Ohio that I mentioned at the beginning of the talk. So just to give you a little bit of background, and we'll talk more about this. This is the East Fork of the Little Miami River here that runs by the site. And this is the site under construction. So this is about a 10-acre wetland complex that's been put in place down there. What it does is it takes high flows off the river and diverts it through a large detention system. So this is basically a large detention wetland type system. And this outlets through a very sinuous wetland channel that you can see kind of making its way in a serpentine fashion to an outlet down here where the water dumps back into the river. Okay, so this is the wetland that we'll focus on for the rest of the talk. And I think the interesting thing about this wetland is that it's entirely reliant on the hydrology, right? So the water level has to come up high enough for the river to offload water into the wetland. So the water is not going to come into the wetland in every single rainstorm the way that it would in this type of flow-through wetland. Okay? Just want to make that comparison. So the nice thing about these floodplain wetlands, right, is that they can hopefully provide you some shock absorption, if you will, in some floods if you were to put enough of these in place. You know you're having a bad day when you're taking pictures from inside a building and you've got a duck going by, or yeah, it is a duck going by. But I think an interesting stat here, right? This is in SI units. I have no idea how many square miles that is. No clue. But that's a lot, right? 232,000 square kilometers of floodplain loss over that 30-year period between 92 and 2019. So this is a worldwide problem, right? We have floodplain loss due to river disconnection from things like diking and levees and the like. So what can these floodplain wetlands provide? Well, they can provide a buffer for high flows, as I mentioned. And this is some work that Bob Holly, who's with a company called Sustainable Streams and out of Louisville, Kentucky, did, and we worked with him on some of this work. This is the Great Miami River, so now we're closer to here in Dayton. I think this is actually the wetland that Donnie was going to talk about tonight if he had been here. So hopefully you guys will get to see him at a later date here at EcoTalk. But the river's flowing from north to south in this picture, and you can see the wetland here, right? The flow rates are kind of colored, right? So the high flows are in red, lower flows in yellow, and you can see that we've peeled off a large portion of water here. The nice thing about these floodplain wetlands is if you design them right and you install them in the right place, they can actually reduce the amount of erosion in the channel and bring that down. It's not going to bring it down to pre-development numbers, but it will bring that erosion rate down closer to a cognate for pre-development, if you will. And that's what he's showing here on the right in a lot nerdier words than what I just said. Okay. So background on this site, and want to thank Bob because he was the designer for this project. Chris Neach with USCPA out of Cincinnati has been involved in this project. Clermont Soil and Water, Clermont Office of Environmental Quality. I think I'm hitting most of the folks that are involved. I just want to thank everyone for the collaboration. This site again is draining through the East Fork of the Little Miami. So this is the East Fork here. The wetland is at the star location, and the interesting thing is just downstream of the wetland is Harsha Lake, which some of you or maybe most of you are familiar with. It's a lake that's there for drinking water supply, and it's also impacted by harmful algal blooms, recurrent harmful algal blooms. The wetland has a watershed of about 234 square miles. Note that not all of the river water is coming through, right? So it's just peeling off high flows during large events. The watershed is 64% agriculture and then a smattering of other land uses, as you might imagine, in roughly 250 square miles. So you can see an example here of one of the harmful algal blooms on Harsha Lake. It is definitely a problem, and so the whole purpose of this wetland was really to try to reduce nutrients coming down the river and ending up in that lake. So East Fork Lake, I think, is another name for Harsha Lake. Current algal blooms in 2009. There's a lot of different things you could do as a land use manager, right? Some of those are hard. This is a large watershed, 200 odd square miles, right? Some of the things you could employ are things like agricultural BMPs. That relies on farmers who are willing to actually have those installed, right? It relies on a bit of social science and challenges in getting people to actually accept BMPs. Septic systems, failing septic systems, conservation of green spaces, stream and floodplain restoration, which is part of this project. A lot of these ag BMPs are really site scale, right? So you're going to put in a filter strip, or you're going to put in a cover crops. So they're small scale. They're not treating a very large area. And so it can be a challenge to get enough of them in to actually see an effect on water quality. So the idea here was, can we put something sort of near the outlet, right? Can we put this constructed wetland in? And the town of Williamsburg was really keen to try this, and they had some land available. And so that's how the partnership all started. Okay, so really the goal here was to look at how well does this thing work for water quality. Our objective was to reduce sediment, phosphorus, and nitrogen transport through the river. So really pretty simple objectives. You can see some pictures of the wetland post-construction here. So this is that really serpentine, sinuous part of the wetland that we affectionately call the gut for obvious reasons, right? Our gut does sort of similar processing as this wetland gut does. Here's the connection to the river. So the river's in the background here, and this is the inlet. So the water has to come over this berm in order to come into the wetland. Okay? And then this is some of our flow monitoring equipment. This is a non-contact laser-based sensor that can measure velocities as the water is coming in off the river and into the wetland. So just some examples of the way that we collect data. One of the other real big benefits of this site is it's located right near a U.S. Geological Survey gauging station. So this gauge is located about 1.5 miles downstream of our wetland. So here, and the wetland site is here. So the nice thing about this is it was able to help us to confirm when we got high enough river water levels in order to have water enter the wetland. Okay? So you can see some examples of these flows here. This is from January 1st of last year through about the end of April. Interesting thing about this wetland is it's a very seasonal system. It really only receives river flows from about the new year through the end of May. Then once June hits, there's high enough evapotranspiration in the watershed, and it's hot enough where the soils dry out in the watershed, and there's not enough runoff coming through the river to actually get the water level to be high enough in the river to get water to come into the wetland. So this is a highly seasonal wetland. It really just receives flow in winter and spring, as I mentioned. Okay. The connection elevation is about 4 foot here. So this is the elevation that has to be exceeded in order for the river to offload into the wetland. You can see in 2024, there were 8 such events, and those are the 8 events that I'm going to focus on. There were about 66 rainfall events in total, not about, there were exactly, we measured it, 66 rainfall events in 2024, and so 8 out of those 66 actually produced flow into the wetland, just to be clear. So what is that, 15% or thereabouts? Okay, a little bit more detail on the wetland itself. This is an aerial view. As you can see, the east fork of the Little Miami River is flowing from west to east in this picture. No, not west to east. North is up, so it's flowing to the south in this picture. But left to right is the point. The water comes in right here. This is our inlet connection. There's a pool here to sort of slow the water as it offloads off of the river and comes into the wetland complex. Then there's a pipe connection to take the water to this detention-based wetland. And what this is essentially an old drinking water reservoir. So there used to be a dam on the river, a low-head dam on the river, and the town of Williamsburg used this as their drinking water reservoir. As late as 2017, okay? 2018, that dam was removed and this reservoir became disused. So the whole idea was, can we reuse this as part of the wetland complex? And the answer was yeah, and as you'll see in the data in just a second, it made a big difference as to how this system performed. Again, the water comes into this pool, there's a pipe connection to take the water in here, there's a bit of sinuosity, and then the outlet to the reservoir is over here, okay? This pipe has a flap gate on it, which is similar to like a tide gate. So when there's water flowing through the pipe, the water can go through, and then when the water stops flowing, the flap comes down, and that prevents the water from this reservoir from flowing back out the inlet. Does that make sense? So it's able to detain the water in that in this abandoned reservoir for long periods of time, as you'll see in a second. The water from the reservoir then drains through this very meandering wetland complex until it hits the outlet over here where the water discharges back into the river. Okay? There's also, during periods of high flow, a bypass channel that connects this inlet pool to the meandering gut. Okay. Any questions on that? Does that all make sense? It's a complex system. Again, the whole thing's about 10 acres. The reservoir is about 3 acres, and the gut is about 7. Okay. Yeah?
Is there a reason why the reservoir is square in shape?
That is a great question that I'm not sure the answer to be honest. It's the old drinking water reservoir for the town, like I said. To give you an idea of scale, these are probably 15-foot tall banks around this reservoir. It's a big hole in the ground. Okay. And I'll show some pictures here. Actually, I'll show some pictures right now for that matter. Okay. So this is during and immediately after construction. It was built in autumn and early winter of 2022 and really kind of came online in early 2023. So this is the reservoir up here. The water's coming in and then goes through the reservoir and out through this meandering channel. And you can see some of the meandering channel being constructed here. Basically, during construction, a number of trees had to come down, unfortunately, but they did reuse a lot of that wood, so you can see wood piles throughout this wetland. They left a lot of wood to try to provide for terrestrial and bird habitat, all of those things. Here's a picture of it in spring during an event. As you can see, the water is coming off the river. You can see how much turbidity, how much sediment's in that water, right? It looks kind of like chocolate milk. And then at the outlet, you can see the water coming, oh, is the water coming in at the outlet? It is, isn't it, right? So this is one of the things that made our monitoring very difficult, right? The water comes in at the inlet, but it also comes in at the outlet, right? And then when the system's draining, on the other side, when the rain event slows down, the water goes out the outlet, but it also goes out the inlet. You follow me there? Because these are all connected directly to the river. So that was a real challenge for our monitoring, and we'll talk a little bit about what that looked like. This is about 1.5 inches rain. You can see that the meanders have connected in some places in the gut, right? This water is actually going over this berm here, and another connection here. So this is what should happen, right? When a wetland gets a lot of water in it. The river level is probably up by 6 or 7 feet in this picture, above what the typical water level would be. I should mention as well, the wetland was planted not with any large plugs or trees or anything. It was just broadcast seeded with a wetland seed mix is what was done. So really the first growing season in 23, a lot of the plants were very juvenile, and really it was this last year in 2024, and now in 2025 we have 15-foot tall trees in there, and just lots and lots of vegetation. Okay, the way in which we monitored this real quick is we had a sampler, the same sort of auto sampler that I showed you in the Dayton work, here at the inlet to the reservoir, at the outlet of the reservoir, in the bypass channel, and also at the outlet to the whole system. So we had 5 monitoring stations that were collecting water quality samples throughout the event. We had an on-site rain gauge. You know how much an on-site rain gauge tells you about rainfall over a 230 square mile watershed? There's some error there for sure, right? We also have established 6 transects. We now have 9. At the time we had 6 transects where we're taking 3 times per year vegetation samples and soil samples to try to understand how phosphorus is being held in the wetland, in the soils and the vegetation. And then obviously doing our part on the water side of things with these automated samplers. We have 8 locations where we're measuring water level. Those are the circular dots that you see here. So really just through the book at this as far as monitoring goes. Okay, hopefully won't lose you here, but this wetland is really complex, right? The water comes in the inlet and in the outlet, and then out the outlet and out the inlet at the end of the rainfall event, right? So the way that we sampled was a little bit different than what we usually do. At 3 of the locations on the inlet side, so the inlet to the system, the inlet to the reservoir, and the bypass channel, we monitored the flow up to the peak. And so we took samples only on this rising limb of the flow at those locations. Okay? At the outlet sampling locations, the outlet of the reservoir and the outlet of the whole system, we only monitored flow and took water quality samples on the declining limb of the flow. Okay? So is there error in that? Yeah, there is. This is the best that we could do at the time. And this is what we're going to base our mass estimates off of, very similar mass estimates to what we looked at in the Dayton unit just a few moments ago. Okay, I already touched on this. 8 inflow events out of 66. So I think we can just move through that entirely. Some practical management issues that we had. I showed you a picture earlier of a lot of sediment in the river, and when that water makes the connection and comes into this pool at the inlet, at the beginning of the wetland, what do you think happens? That river water's got a lot of velocity, right? And then it kind of makes a left turn and it comes off into this wetland. What happens to that velocity? It goes down, right? So what happens when water velocity goes down? Well, its ability to entrain sediment and hold it in the water also goes down. Right? So what happens? Well, literally many tons of sediment deposits right there. And that's what used to happen, right, in our floodplains when we had connections between these rivers and their floodplains. Is those floodplains would be areas of massive amounts of deposition. We're talking about meters of deposition over hundreds of years, right? So this is supposed to happen, but it's also a pain in the rear end because it means you have to actually manage it, right? So if you don't manage it, what happens? Well, the sediment builds up and up and up and up and up, and then there's less and less frequent events that actually offload into the wetland. Does that make sense? So what this means is, the designer was thinking, hey, this wetland is going to see rainfall come in or flow from the river come in about 30 times a year. And what we saw in 2024 was only 8, right? And that's because of this buildup of sediment at the inlet. So once or twice a year, we have to go in with an excavator and dig out that berm that starts to build itself. Okay, so that's one of the management challenges in this type of wetland. There's some work being done, some modeling being done right now to try to rework this inlet. It's going to require us to get some grant funding to do that, but that's in the potential cards down the road. Okay, so I mentioned there's 8 inflow events. I'm going to show just probably 4 or 5 slides of data here, looking at those 8 events because I think the data are pretty cool. These are all from 2024, as I mentioned. All of the rainfall events are here, so you can see it took at least about a 7/10 of an inch rainfall event to get water to come into the wetland. And we had some events that were up over 2 inches, so some very large events as well. The inflow volumes, the flow that we measured coming in the inlet here, are massive, right? We're talking about millions of cubic feet of water, many millions of gallons of water coming into this system. The thing that I really want to highlight, though, is these last 2 columns. Okay? There's this idea of residence time in any treatment system, right? You can think about this for water, you can think about this for any pollutant, air quality. There's an idea of residence time, right? You hold on to the water for a certain amount of time, and therefore you should get this amount of treatment. If you hold on to the water for 2 times that amount of time, you should get more treatment, right? And if you hold on to it for less, you should get less treatment, right? And those things are related. Maybe not linearly, but they're related in some way. So what I have to here in these last 2 columns is the residence time for the wetland in hours. This is the reservoir, the drinking water reservoir that was reused as this portion of the wetland here with the flap gate, right, that I talked about earlier. And you can see the residence times, right, for the events. And then the overall system residence time, the whole wetland complex, is here. What do you know about the reservoir residence times relative to the whole system? It's like really close, right? So what does that mean? Well, that means that this reservoir is slowly bleeding water out into this gut. It's giving it enough time to actually have those nutrient processes happen in the gut. What would happen if this reservoir was not here? Well, the river would offload water as the water level rises in the river, and then as the river drains out, you can bet that water is going to drain out into the river just as fast, right? So this reservoir is really a critical component in that it provides us with enough storage and enough sort of dampening of the flow, right, to then bleed the water out at a slow rate over a period of days, many days in some cases, right, to provide for that pollutant treatment. So we really think that this reservoir is a critical component at this wetland. It's a unique one here, but there are many hundreds of these types of drinking water reservoirs that exist across the state, some of which are still in use, by the way, others of which are disused like this one was. Okay, I'm going to show you data for sediment, nitrogen, phosphorus, because that's what I told you the goals were here. What we're going to look at is concentration on the left. So this is all concentration data, milligrams per liter, and this is mass over here in pounds. Okay. What we have is the inlet to the system. So this is the system inlet here, where the water first comes in off the river. The reservoir inlet, where the water enters the reservoir, right here. The bypass channel, which is this monitoring point, where the water is bypassing between this pool and the gut. And then on the right-hand side of these dashed lines is the effluent side. So reservoir outlet is this point, and system outlet is the point where the water dumps back into the river. Okay, does that all make sense? What you're going to see, right, is as the water passes through the wetland, we get vast declines in concentration from upwards of about 700 milligrams per liter of sediment in the river water down to less than 50 milligrams per liter on the outlet side of the wetland. So lots of sediment dropping out. And you can see the mass here is in the hundreds of thousands of pounds. So we're talking about literally hundreds of tons of sediment dropping out over these 8 events. It's a huge amount of sediment that's being peeled off of the river. Similarly for phosphorus, you can see that maybe the trends aren't as stark, right? But you can see some cleaning of the water as it goes through that initial pool here. And then certainly as we give it the many hours of treatment in either the reservoir or the reservoir and the gut, we get concentrations that have declined by a factor of 5, say, right? From upwards of 1 milligram per liter coming in to about 0.2 coming out on average. And in terms of mass removal, we're removing hundreds of pounds of phosphorus over these 8 storm events. So it's able to really hold on to and process a lot of phosphorus. Similarly for nitrogen, you can see inflow concentrations inlet side over here, and then effluent over here, so the cleaned water over here. Again, roughly a 50% reduction in this case in nitrogen, and again, hundreds of pounds of nitrogen removed across the wetland complex. So, really, really good removals, and I'm going to move through this kind of quickly because it's, I've kind of walked through the removals already, but they were similar to other wetlands in the literature, including the Olentangy River wetlands in Columbus that have been studied for the last 30 years. So that was exciting to see. So in terms of total retention of pollutants, you can see across these 8 events, just under 2,000 pounds of phosphorus, about 3,400 pounds of nitrogen, and over 1 million pounds of sediment. So just huge numbers of pollutants that have been able to be stripped off of this river flow. So what does all this cost, and is this effective? Is it an effective management strategy, right? You can't really figure out ROI if you don't think about dollars and cents in some way. And so here's the breakdown, right? The initial design, about $40,000. There was some redesign. Basically, we got one grant, and we were able to dig down this much to put the wetland in. And as you get another grant, you can dig down the connection elevation more, right? The main cost in building this is moving soil, basically, and trucking things. Construction, so anyway, there was some redesign that was done, so you can see that here. Construction was just over 600 grand. And so in total, we're in the neighborhood of $700,000 across this project, okay? In terms of cost to remove pollutants, this works out to about $208 per pound of nitrogen, about $400 per pound of phosphorus, and just over 50 cents per pound of sediment, okay? That sounds like a lot, like there's no context to that, right? But I've mentioned all these H2 Ohio wetlands that have been built. There are about 10 of those that have similar monitoring to this, maybe some differences, but similar level of monitoring to this. And this one has the second best ROI of those 10, okay? And this is only in the first year, right? This wetland's gonna continue to perform and function for decades to come if we maintain it and keep it up. So these costs certainly will come down over time. Okay, where am I on time here? Oh, okay, perfect. We're finishing up right on time. So the long story short here is this thing was highly effective. We think this is a very large watershed management tool that can be applied on river basins across the state. It certainly enhanced pollutant treatment. We continue to monitor in 2025. And we have funding to monitor at least into 2026, and we'll see we have some grants out right now that we've written to continue monitoring maybe for another couple of years thereafter. So this thing worked really, really well. It was very complex, obviously, to monitor, but we think that it's an example of a wetland type that is underutilized, both here in Ohio as well as in other states, that could be it's not maybe a new tool in the toolbox, but a rediscovery of an old tool that can help to better manage nutrients in our watersheds. So I'll stop there. Do we want to take questions now? If there are questions, okay, awesome. I'm happy to take any questions if there are questions. Yeah.
So the silt deposits that have the phosphorus and nitrogen in it, so that gets removed once or twice a year. What do you do with that? Where does that go?
Yeah, so the sediment that builds up there at the inlet where the water first enters the wetland, we've done some analysis of it, it's 90+% sand. Because that's the heaviest particles in the water. And so when the velocity goes to close to zero, the sand just immediately drops out. So if you wanted to create like a baseball infield or 10 with that sand, you probably could do yourself some good, right, if you mix it with some clay. But no, what really happens is we end up spoiling it up on the banks. So we just leave it on site and let it revegetate, basically. So that's what's been done so far. Because it's dump truck loads, plural, full of sediment that gets deposited each year. So otherwise we'd have trucking costs. So far, I think I had that on the slide and I didn't mention it. Yeah. So far, the maintenance has been about $3,000. That's all we've spent on maintenance, and that's been primarily on removing the sediment deposits. I meant to show. I have acknowledgements. I think I mentioned all these things earlier. I meant to show there is a bald eagle nest on site, and that right here is one of them sticking its head out there, which is cool, up in a sycamore tree on site. So it's really heavily used by birds. It's a great spot, hidden spot that nobody knows about. That when you're out there on your own, you can see all kinds of interesting bird life.
I'm just curious, with the monitoring equipment that you have out there, is that when it's monitoring your nitrogen and your phosphorus levels, is it like taking a reading like every hour or every minute, or how does that work?
No, the auto samplers, basically they have a pump on the top, a computer, and then underneath it a hollow chamber. And there's tubing that runs down to wherever you're trying to sample the wetland, and the pump turns and it pulls the water up from the wetland into the sampler. And then we have a really expensive container in the bottom called a bucket from Lowe's that that the water dumps into, literally. And then after the rain event, we go out there and we honestly we ship the samples over to the US EPA lab in Cincinnati, and they do the water quality analysis.
It's like a mass spec or something.
It's you're testing me here. The nutrients are done on, I think, on a seal is what the instrument is called. And the sediment is all filtration, vacuum filtration, just measuring the weight of the sediment in the sample. Yeah. So it's all, to answer your question fully, there's no real-time water quality monitoring. It's all samples during the event and then post hoc analysis.
Okay.
What year did you say the construction was finished?
It was, so it was impacted by bats, of all things. Some of you in the audience are probably way more knowledgeable about bats than me, so I'm going to apologize in advance. There's a bat season during which you can't do construction when they have babies, is that right? Before they can fly, I think? Yeah. I had an issue, this is another story, but I had an issue in my house one time where we had bats in our attic, and they had to put a one-way valve in, and the bats lived in our house for like another 2 months because you can't kick them out. Anyway, yeah, you guys probably know that version. It was fascinating to me, knowing nothing about bats. Anyway, we weren't able to construct until, I think construction started in October of 22, and the finished grading was finished in December, so it was like a couple of months of work. I would have to look back at how much earthwork there was, but it was hundreds and hundreds of dump trucks in and out of the site. As you might imagine, to bring this whole site down to the river elevation, there was a lot of soil that had to be moved. Much of that soil was really sort of historically kind of mucky and just not very agriculturally fruitful. So the city was willing to use it for this wetland, and a lot of that mucky soil got taken to local agricultural fields, and the farmers were willing to take it as like sort of top dressing for their field. wetlands.
So we wash back down again.
Yeah, no, ideally provide some nutrients for the corn and other things that were growing, soy and all that.
Yeah.
So a lot of it was land applied in fields, ag fields locally. To
Sounds
reduce-
like I envision like all the riverine invasive species like moving into that environment. Was that an issue?
That's again outside my area of expertise. I would imagine that there are invasive species that have moved in. The one comment I can make about fish is that they certainly get moved into the wetland during these high flow events. There's no doubt. And the reason why I know that is if you go to this site a week after an event where the river gets to 6 or 7 feet water elevation, and then drains back out, a lot of the fish get left high and dry, right? So the eagle, which actually I got the location of the eagle wrong. The eagle is up here in the, I know it's, there it is. Loves it, right? Because it's like a buffet. The fish are flopping around, and so you find fish carcasses everywhere all of a sudden. All right. Well, thank you all very much for listening. I had fun, enjoyed being here, and I'll pass it back to Lisa to introduce our second speaker. Thank you.